In this video, I want to talk about the second part of the sensitivity report that is related to the constraints. And in this part, we have something called shadow price that we want to understand better. So first, let's look in details. There are three constraints. All of them in this example are resource constraints: number of pumps, labor hours, and feet of tubing. The available units are the right-hand side values. We have 200 pumps, 1566 labor hours, 2880 feet of tubing. And actually, we know how many units of each resource are used. They are here in the final value. So you see all the pumps are used, all the labor hours that are available are used, but not all feet of tubing are used. We actually have a slack, and you see what's in the answer report that shows here as 168 or 0 slacks can actually be easily calculated by taking the difference between those two columns, right? But we also have something called a shadow price. And what is the meaning of shadow price? Well, a shadow price tells us how much the objective function value would change if the right-hand side of the constraint changed by 1 unit, right? And it's a rate of change. So basically, if I increase the right-hand side by 1 unit, the objective function will increase by 200. It's a coincidence that, right, the right-hand side here is 200 and the rate of change is also 200. You'll see here it is different, right? It is for every one labor hour that we had more available for the production, we would gain $16.67 in the profit, right? And then if we lost 1 hour or several hours, for every hour that we lose, we would lose this many dollars as indicated by the shadow price. So this is a kind of marginal value. And again, you see why the name sensitivity, where the name sensitivity analysis comes from. It tells us how sensitive are we to this resource, right? If we had one more unit and it said here, for example, you gain only $5 for it, we would say it's not very important, right? If we gain some units or lose some units, it's just $5 of profit per unit for every unit. With the total profit of 66,100, that's not a lot, right? But if this shadow price is very large, right, for something like just one pump, we gain $200. Maybe that's more significant for us. If it was even larger, it would be even more important, right? So the shadow prices are very interesting because they tell us the rate of changes, and they tell us also in what range, this report tells us in what range the shadow price works. So this $200 for an additional pump works for up to 7 pumps extra, right? So if we were to increase the available pumps, the right-hand side, by at most 7, we gain $200 for every pump. If we were to decrease the number of pumps by at most 26, the shadow price works. We could determine $200 for every lost pump up to 26 pumps. The same thing for labor hours. We have allowable increase, decrease. And the interesting case is also feet of tubing. Well, feet of tubing tells us if you were to get more feet of tubing or reduce them by up to 168, then you wouldn't have an impact on the profit. Well, why is this? It's easy to see that we are not using in our optimal solution all the feet of tubing. There is the 168 units of slack. So if you were to add more feet of tubing, it's like you were adding a resource that you do not really need more of, right? You're adding something that anyway you have left over, right? Why is that? Well, the reason for this is that the pumps and labor hours are the constraints that are binding the optimal solution, that are limiting the improvement. This optimal solution was determined by profit maximization that basically hit the wall with these two constraints. And then it couldn't improve this solution more. It couldn't find a higher profit because of those two constraints. The feet of tubing was somewhere such that it wasn't limiting the improvement, and therefore getting extra units of feet of tubing will not give us any increase in the profit. But getting extra pumps and labor hours will get us extra units, dollars of profit. Now, the important thing also is to realize how do we get those extra dollars of profit? Well, we don't get them directly. If you give me 5 more pumps, what we will need to do is we will need to resolve the problem, and then there will be a new optimal solution. I don't know what this new optimal solution will be, but I know that the impact on the profit will be that those 5 new pumps will give me each $200 of profit more. So let us now consider an example to see if we understand. Suppose that 190 pumps are available instead of 200 pumps, right? So imagine, let's say, a supplier delivered some pumps to us, but we found out 5 of them are broken, and now we need to revise our production plan, but we still want to maximize the profit. What would be the impact, right? So, like I said, we would need to resolve the problem to find out the new optimal solution, but we can determine the new optimal profit without resolving because we have the shadow price and we know the allowable increase and decrease. So this is a decrease of pumps, or right-hand side of pumps constraint by 5, right? And then we have to compare it to the allowable decrease, which is 26. So we need to say this is less than or equal allowable decrease, which is equal to 26 for this constraint, right? We're considering pumps constraint, right? So what do we know from this? Well, so the shadow price can be used to calculate the change in total profit, right? So I can now say the total profit will decrease by, well, since I decreased the right-hand side by 5, I'm also decreasing the profit by 5, the same 5, multiplied by shadow price, right? And so I'm going to say 5 pumps times the shadow price is 200, right? This 200, but this 200, I'm going to put a unit. It's $200 of profit per pump, which is the unit of constraint, right? So if this shadow price is $200 per pump, this is $16.67 per labor hour, and this is $0 per foot of tubing, right? So this is going to be $1,000. Notice there is pumps times dollars over pumps. So pumps disappear and the profit increase is just measured in dollars, right? What else can we say? Well, since the profit is increasing, right, but we haven't changed the profit per unit of Aquaspa or Hydrolux, but we now say this total value of this objective will now be $1,000 more, so it will be $67,100. How can we achieve this? Well, it must be that the optimal solution is changing, right? Since the optimal profit changed, the optimal solution must be changing too, right? So let us see in Excel what this looks like, right? So we can convince ourselves that it works by resolving the problem in Excel with changed value. So let me go to the model here and then change the right-hand side as we did, decrease it by 5, so make it 195, right? Again, this does not update automatically. I need to go to the solver and I need to click solve again to resolve the problem. And then observe what happens here when I resolve. When I resolve, the solution changed, right? It was 122.78. I couldn't have predicted it will be 132.63. But what I did predict is that there will be a $1,000 decrease in the optimal objective function value. And you can see, right, this total profit, which was before 66,100, it is now 65,100, which is exactly what we predicted. For every one pump, we lost $200, so a total $1,000 was lost, right? I'm going to cancel this and bring back the number of pumps to 200, right? So by analogy, of course, I could consider, let's say, an increase, right? What if 5 extra pumps, or let's say 10 extra pumps are available, right? So now it's not a decrease, it's an increase of right-hand side of pumps by 10. We will have to see is it less than allowable increase? What's the allowable increase here? Its allowable increase is 7. So in that case, this is not, right, less than or equal allowable increase. So the shadow price may not be used to calculate the change in total profit. So I cannot just say, well, there will be an increase by 10 times shadow price, right? 10 times 200 $2,000. $2,000 is not going to be the gain and the profit. No, 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 right? Why? Because I'm now outside of the allowable increase, right? The allowable increase is 7, so it tells me for the first 7 pumps, the shadow price works if I have extra 7 pumps. But if I have, right, this is question 4, if I have extra 10 pumps, I don't know what will happen. How much will I gain? Will I gain anything at all? We don't know, right? So this is incorrect. I shouldn't be considering this increase. I shouldn't expect to gain $2,000 for an extra uh, 10 pumps, right? But actually, I should still expect a change in profit, and the optimal solution probably will change too. Again, we can convince ourselves by looking at the looking at the original model and then changing this value to 210, right? Maybe let's change it to 207, and let's see that if we now resolve the problem, right, we get a solution 108.99, and we do the optimal value increases from 66,100 to 67,500, which is by 1,400, right? 1,400 is 7 times the shadow price, right? This is exactly what we would expect, right? But if I increase this right-hand side by further, don't change this, change the right-hand side, to 10, right? And I solve again, and notice what happens. Nothing changed. The optimal solution is still this, right? So I'm still using only 207 pumps. I'm actually not using 210 pumps. Why is that? Well, actually, it is because the feet of tubing now became a binding constraint. Notice we are using maximum labor hours and maximum feet of tubing, and now the pumps has a slack of 3, right? Remember what I did is I did click solve here. The solver gives me the best solution considering 210 pumps, and I'm not getting $2,000. I'm just getting the dollars for the first 7 pumps. It's not always going to be like this. It might be that I would be still getting something for those extra pumps, but I shouldn't expect those additional 3 pumps above 7, above the allowable increase, to give me the $200. They could give me something less. They could give me $100 or $50, or in this extreme case, they give me no increment at all. So let me actually bring back this model to the original 200 pumps. And let us now consider what happens graphically. So here again is the graphical interpretation of the problem, and we're going to focus on the pumps constraints. So I'm going to, for a moment, hide the profit level curve and just show you the red line for the pumps constraint. So notice the pumps constraint and the labor actually were the binding constraints. And you can see those constraints, they are the ones that on the intersection of which the boundaries, right, of which determine the optimal solution. So what happens when we, let's say, decrease the available pumps, right? So if I have here 200 available pumps, if I now decrease this by 1, observe what happens to this solution. If I decrease it, the line shifts, right, a little bit down to the left, and the solution follows. And notice that the solution keeps changing. Right, let me go back to 200. Right, if it's 200, it goes to 199. The solution changes. Actually, it changes in a certain predictable manner. It was 122.78. It increased here by 2. It decreased here by 3. And the net effect is $200 less, right? Every pump I decrease is $200 less. And as I decrease, you remember the allowable decrease was 26. Let me decrease by 26. This is now decreased by 26, right? It is now the x2 is 0. As I decrease more, I no longer get a rate of of $200 per pump. Now, right, $60,900. If I take one pump less, it becomes $60,550. It actually decreases by $350. So you see, for every pump now, I'm losing $350, not $200. Why? Because I went beyond the allowable decrease of 26. Right, the $200 rate per pump works only if I'm within the allowable decrease. And the same thing what they did with allowable increase. If you recall, we went from 200 and started increasing, and then we said up to 7, allowable increase is 7, up to 7, the allowable increase works. We gain $200 per pump. We gain here a total of $1,400 for the first 7 pumps. But as we increase further, right, when I go to 10 and more, there is no gain. Look what happens to the solution. The solution is still here. Why is it not moving anymore? Well, because there is another constraint, the tubing constraint, that suddenly started playing an important role, right? Now it's the labor and tubing that are binding constraints, and pumps we have too many of. We are unable to use them because the other constraints are now limiting the production, and the rate of improvement in the profit became zero, right? Zero extra dollars for extra pump. So this is the graphical interpretation. So why are those shadow prices important for us? Well, remember that a constraint, something that's a constraint now, could become a decision variable at some point, right? If I have a constraint on the pumps and I realize there is a great opportunity to improve my profitability by having more pumps, I actually can consider how to obtain more pumps and see if the cost of obtaining them is small enough to justify getting more of them and increasing my profit. Right? The same thing for labor hours. If I were to get more workers, right, I would gain some more profit from that. Is that worth it? Right? The shadow price helps me evaluate this.